knowledge to the question. So question will be of practical or problem solving kind of thing, right? Now problem solving can be done in multiple ways. I can ask you to I can ask you to answer in case of multiple choice also, but that answer will be something where you have to understand something from the question, right? So I'm not focusing, or I'm not saying what type of questions will be there. Type of questions can be MCQ, multiple selection, can be short answer, whatever it may be. But the point is that it will be testing your understanding rather than testing your remembrance.
And sir, will there any negative marking?
Yes, there could be.
Okay, sir. Thank you, sir.
Okay, so let me start. Okay, so in the previous lecture, where we left off was, I believe, this particular slide. What we were looking at was the buffered I/O. Now, in buffered I/O, also you have multiple ways of reading data or writing data into the file. Okay, so if you have unformatted data, which may be in the form of lines or characters or something, or maybe a number of bytes, you can also use the buffered I/O to read that kind of data. So, for example, you have a getC or fgetC are the fgetC and fgets are the kind of system calls which will allow you to read one character at a time or one string at a time. When we mentioned string here, it basically means that until a null character, right? So you read until not a null character, until a new line character. So you read the data until a new line character here. You read the data character at a time here, and then here you can specify the size, right? Fread will allow you to specify the size of data that you want to read. So as I said, getC, fgetC, you provide the file pointer, it will allow you to read one character at a time. Also, there is an equivalent function for getChar. So in the getChar also you can provide the standard input pointer to read the data from the keyboard, or else you can provide the file pointer to read the data from the file. You can check for the error, while reading or writing, or you can also check for the end of file. So there is a special function that is given in the buffered I/O case, where you can actually check for the end of file. Whereas in case of unbuffered, you always have to issue the read command, and if the read system call, and if the read system call returns you 0 value, which means that it was not able to read anything, and then you have to assume that you have reached to the end of file, right? Whereas here you have a special system call to check for the end of file. Writing the character, similarly, you have these three options, right? PutC. So PutC basically you can provide the file pointer here, or you can provide the standard input over here, or you can use fputC, which again will take the file pointer here, and you can provide that information. So by default here the reading will be done from the standard input. Here by default the reading will be done from the, or writing will be done, from the file pointer, which is provided over here. So again, I've given you the code. I'm not going to run it right now, but you can, these are all simple code which just implements these functions, and you can just run them and check the output. These are the line at a time commands or system calls, right, where you are reading, until the new line character, and this will be basically reading one line at a time, right? So this is going to be reading from a keyboard. This is going to be reading from the file. And then here you can do the writing same way, right? And these code is provided to check for the those functions. Now this slide is something that is I want your attention to. So what I've done is, if you look at this code IOefficiency.c, which is what I've provided to you, what I've done is I tried to copy a file. Okay, I tried to copy a file, but I had used different functions for copying. Okay, so the way I tried to copy the file is I basically provided the redirection input was provided as this file. So I said that the data you need to take is from this file. The data you need to write, right, is into this file. This is basically allow you to copy the file, right? So you take the data from here, which is your standard input. Your standard output is going to be this file, which means it is allowing you to copy the data from this file to this file by using your standard input and standard output. Okay, and in this code, all we are trying to do is we are trying to take the data from the standard input and dump it into the standard output. But this code is implemented using three different set of functions. So in one of the code, we used read and write command, simple read and write. So this is the unbuffered IO commands. Okay, then we used the character by character reading and writing. Okay, so fgetC and fputC, right? So this is character by character writing, but buffered IO, but using the default buffer. And so we use the default buffer and we use this functions. Then we use the string based or line based IO functions, and I increase the size of the buffer. So what I want you to see is this one. This time is utility which allows you to which basically gives you the total running time of a program. Okay, so this time will say how much time this executable took. So if you see that when we use unbuffered IO, it took 6 minutes and 27 seconds, right, to copy this 2 MB of file from here to here. Okay, whereas when you look at the buffered IO, but character by character, it took only 0.19 seconds. And then when we increase the size of the buffer and then we did line at a time, it was further reduced to 0.14 seconds. So what I'm trying to say is that when you use unbuffered IO, you have to be very careful when to use unbuffered IO. You should use unbuffered IO only in the cases where you cannot use buffered IO, generally speaking, because as you can see, unbuffered IO is very, very, very slow compared to the buffered IO. Even if you do character by character copying, right? Even then, the difference is significant. Okay, so the point is that you should try and avoid unbuffered IO if possible, and use the buffered IO. Okay, that is the learning thing from the buffered and unbuffered IO stuff. Why that is? Because as I said, every read and write operation here will have to go to the disk, and whenever you go to the disk, the operation slows down, right? Whereas here it is using an internal memory first, even though you are doing character by character, but there is a 1K of buffer. So 1 kilobyte of buffer data is still in the memory. Okay, and so 1 kilobyte of data is in the memory from the standard input and one kilobyte from the output, right? So you basically are using like 2K buffer, right, for reading the data and writing the data, and therefore even though you are doing one character at a time, the speed is much higher. Okay, this is something that you should notice. If you want to read a fixed size items from the file, right, there is a fread and fwrite functions that are provided to you. So what you have to do is you have to provide the size of each item, and then you have to provide the number of items, right? So you are basically providing two information. So here you are saying that my size of the item is the size of the buffer, but then I'm only going to read one item, right? Whereas here you are saying that my item size is 1 byte or 1 character, and here we are saying that number of items I am reading is the size of the buffer, right? So even though it is reading the same number of bytes from the file, there is a difference in in these two calls in terms of number of items and the size of each item. Same thing you can do for the write. And then lastly, these two functions, which you may have seen, you may not have seen. We have been using scanf and printf for C programs for quite a while, right? But generally speaking, we use them only to read the data from a keyboard and display the data on the screen. However, there is an equivalent functions for the file operations. Okay, so if you use fscanf, it is the same thing as scanf, except the difference is that the reading will be done from the file stream rather than from the keyboard. Okay, same thing with fprintf. So you can use fscanf and fprintf to actually read the data of the C data type formats. So remember, I told you that the buffered IO allows you to read the data in the C data type format, which are these two functions. Okay, so these two functions are again very important. If you want to read the data in the format of C data type, then you can use them to read and write from the file. So this is all about the IO functionalities. Okay, any questions you may have for file IO that I can take? Okay, so if there are no questions, let me close this and open the chapter for process management. Right. So this is the next topic that we are going to learn, right? Process management. And now, you will see that from this chapter onwards, this topic onward, we are moving more towards the operating system and kernel style of programming. Okay, so till now, we basically learned very basic programming like shell programming. We learned basic C programming. We learned, IO level stuff, but they were not really diving into the operating system level stuff, right? They were more on a user level stuff still. Although in the file IO, we did try and understand how the operating system keeps track of open files for different processes, right? So that is one area that we only looked at from the diving deep. However, here you will see that from this chapter onwards, we will be mostly diving deep into the operating system level stuff, where we learn how certain things happens, internal to kernels and to manage different processes, to manage different threads, and so on, right? So first of all, what are we going to learn, right? So when you talk about process, right? What is a process? So let me talk about that first, and then I'll come to the system call hierarchy. What is the concept of the process, right? So the concept of the process, in short, right? If I have to give a very succinct, definition of a process, very small definition of the process or short definition of a process, it means that a process is a program in execution. That is the definition. So any application, any program that you may have on your computer, which you run it either by double clicking on that or by typing that application executable name in the terminal window, or maybe you are running in a different way, which I'll show you how to do that. So you could actually run application in multiple ways, but whenever you run an application, whenever you execute an application, that execution that becomes a process. Okay, and we have seen that if you go to the terminal window and if you use a ps command, right? So it basically shows two processes which are running. So here you have the process called bash, which is basically our terminal window, and this is the process ID for that. And then we are running the ps command, right? Process status command, which is running currently as a process ID this, right? 2986. Now, instead of that, if I do ps ajxf, then it shows whole bunch of processes, and the reason is that when you just run ps command, it only shows the processes running for a current user, the user which is logged in. That's it, right? On this particular terminal window. However, when you do ajxf, it shows all the running processes on your system, right? All the running processes on your system. Okay. So this is the reason you will see whole bunch of processes, because all of these processes are currently running. And when I say process, you have to immediately understand that there is some program, there is some application which is running, and it has basically the process ID. So this PID column is indicating the process ID. PPID column is indicating the parent's process ID. Okay, so this one is the parent's process ID, this one is the current process ID. And what program or what command that you have executed are these, right? So these are the commands, or these are the programs which are running, and these are the process IDs for them. Okay, so that is basically the process. Whenever you run a multiple instance of the same program, they are a different process. So for example, if I run multiple ls commands on a different terminal window, each one will be different process. Even if I run ls multiple times on the same terminal window, each one will have a different process ID. Okay, that is what the process means. Now process has two kinds of memory area allocated by the operating system. One is the kernel address space, and kernel address space, we as a user do not have an access to the kernel address space directly. We cannot access that area. Operating system will restrict you to access that area, and why, I'll come to that later. Another one is the user address space. In the user address space, you have the data, right, which is your variables that you have declared in your program. So that data area is there, and then there is an executable program code which is there. Okay, so program code and data area is in the user address space, and then there is a certain information which operating system maintains, which will come to that is maintained in the kernel address space. And if you see here that there is a word called context, so that context is what the kernel address space is. This data and this program code is basically your user address spaces. Okay, so you have the process list, right? So you have main memory has a lot of processes. The processor, right? The processor which is running a particular process, it keeps track of certain information here. So it keeps track of PC. The PC stands for program counter. You probably know that, right? So it is basically telling you which is the next instruction to be executed, which is your program counter. The limits of memory. So it basically keeps track of which starting address in the memory and which ending address in the memory this process belongs to, right? So this process has a fixed amount of memory allocated, right? And if you need more memory, the process needs more memory, it will allocate more memory, and then it will increase the size accordingly, right? The limit will be increased over here. The base will remain the same, limit will be increased. And there are other kind of registers which are your processor registers, such as you have a stack pointer, you have the process status word, you have information about open files, and all of that will be there in the context. So what are we going to learn, right? So process management, when it is implemented in the operating system, it allows us to use certain system calls. System calls are nothing but the library functions implemented by the operating system, which we generally term as a system call, right? Because we are calling the function which are inside the system, implemented by the system, right? So in the process management, these are several functions that are available to us, and we are going to look at most of them as an examples, right? So we are going to look at the practical examples of each one of them. Whenever you have multiple processes running on the system, obviously there has to be a way for communicating between the process. And there are three ways to communicate between the process, one of which is called signals. So in the following chapter, or the next couple of chapters after this one, we're also going to learn about the signals and the system calls about the signals. Okay. So this is all about a basic, information on the system call, right? So now let's learn more about what is a process and how does operating system maintain certain things. So the process has what we call context. Now, context part is divided into two areas. Okay, one is called process control block, and the other one is a stack. Now, you might be knowing that stack is a memory area of a process where whenever you declare a local variable to the functions, or whenever you pass a parameter to the functions, that information is in the stack. This data area is basically your heap area, and heap area is where your global variables are usually stored. PCB is the area where the operating system will maintain certain important information about the process. Okay, so you have a process ID that is also part of PCB. Parent's process ID is also part of PCB. You have a process state. I'll come to that in next 2-3 slides. You have the CPU state information, right? So you have the content of the CPU registers. You have a special register called PSW, which is what we call process status word. So where you have the flags like 0, carry, overflow, all of those information is there in the process status word, which I believe you have studied as part of your computer organization course. You have the priority about the process and the scheduling information about the process. You have to keep the pointers to the memory area. As I said, you have to keep track of the base and the limit for the memory, right? So how much is the space allocated for data area, program area for this particular process, right? Open file information. Signals you have not studied, but we'll come to that later. Time accounting information, right? So how much, when was this process created? How much time did it took off the CPU currently? So basically what will happen is that in case if the process takes more time to run, it is not always that a single process will continue to run on a on that particular processor or a core indefinite amount of time. Okay, so usually you may have heard about. Have you guys studied a little bit about context switching?
No, sir.
No. Okay. So let me talk about that. Let me actually draw a picture for you. Okay. So what happens is, let's say, let me draw a timeline first. Okay. So let's say my computer has 2 cores, right, or 2 processors. I'm going to call that C1 and C2. And let's assume that there are, so these are cores, okay, or processes or processors. And then I have I have 3 processes. Okay, so let's say I have P1, P2, and P3. These are the 3 processes. Now, obviously, I have more process and I have less number of cores. So how do I ensure that I run all the 3 processes even though I have a small number of cores? So one option obviously is that I allocate, let's say, these 2 processes to these 2 cores, and then I wait for one of them to finish, and then I allocate another one to the available core. But what is the problem? Let's assume that this process takes 10 minutes. Let's assume this process takes 20 minutes. That means for 10 minutes, there is no progress of this process, which is not allowed, right? Meaning that a user who has started this process cannot wait for 10 minutes to finish this. Maybe this process only takes 1 second, okay? But that process taking 1 second will have to wait for 10 minutes for one of these 2 to finish, which is not allowed. So what operating system does is they call it as time slicing. Time slicing. Okay. So there is a fixed amount of time allocated to each of the processes to run. So let's assume that the time slicing is done at 10 milliseconds, or context switching. Okay, time slicing, context switching. I'll come to what context switching is, but context switching is done at 10 milliseconds. So what will happen is this timeline, I'm going to divide here 10 millisecond 20, 30, 40, 50, and so on. Right? So these are all milliseconds, 10, 20, 30, 40, 50. So let's assume that initially I started, let's say this process takes 15 milliseconds. Let's say this process is taking 30 milliseconds. And this process is taking, let's say, 5 milliseconds, assuming that, right? So what may happen is maybe these two processes are allocated here. So let's say C1 is given P1 and C2 is given P2. Now, these two processes will run only for this 10 milliseconds. Now, because these two are longer processes, it's P1 still requires 5 more milliseconds and P2 requires 20 more milliseconds. However, we cannot keep both of them running in the indefinite amount of time. So what we will do, or what operating system does, it does context switching. So context switching means that whatever the state of running for these processes are, it will be saved into the memory. Okay, so the processor data, the data in the registers, processor status word, and all of that information which is there, right, inside this core, it's going to save that into the memory. So let's assume that P1 is being context switched. Okay, so if P1 is being context switched, so during at this time, the register content and the stack pointer, the program counter, the PSW, all of that information will be saved in the memory, temporary area. And then C1 will now get P3. Okay, and C2 will, let's say, continue to run P2 because there are no more processes to run. If there was P4, then again, this C2 may be allocated to P4. Okay, now at the 30 milliseconds, okay, or actually at 25 milliseconds, it must have found out that my, so at 25 milliseconds, it must have found out that P3 is finished. Okay, so depending on the implementation of the operating system, either at that point or maybe at this point over here, now P3 is done. So I can actually use this core again to allocate to another process. And assuming again we only had these three processes, again what will happen is that C1 will get execution of P1 and C2 will continue. Okay, this swapping of the processes, right? And when P1 has to start running again what will happen? The temporary information, the status information that was saved in the memory will have to be brought back into the processor's registers, right? So the data will come back to the processor registers, program counter, stack pointer, PSW, everything will come back to C1's registers, and then it will start running from where it was left off. So the point is that switching part that we are doing, right? That switching part is what is known as context switching. You are changing the context of the processes. Okay, you are swapping or switching the context. Okay, this is how usually the process is run, and therefore, even though you may have more than 100 processes, 200 processes running on the system, all of them appear to run simultaneously. See, on my laptop, I only have 6 cores, right? But when I did that PS, right, I had hundreds of processes running. How does operating system make sure that no process is waiting longer time? By doing this. So this is what, when you run the programs, when you run the applications like this is what is known as concurrency. Concurrency. So concurrent process means that you are running more processes in limited number of resources, limited number of computation power by doing this context switching. That is what is known as concurrency, because you are telling user that I'm running everything in parallel, but in reality you are not running everything in parallel. right? You are running some part in parallel and then some part, again you will run like this. So there is a difference between concurrent and parallelism. Parallelism means that you only have two processes to run on a two-core system. That is what you call parallel, because both the processes are running exactly at the same time on two different cores. However, concurrent means that you may be running the n number of processes which are equal to the n number of cores, but then other processes are still waiting for them to get the processor allocation, core allocation, right? So but you are making the user perceive, right? The user is kind of understanding that, hey, once I submitted the application, it's still running, right? So if you look at this point over here, actually P1 is not running, but the person who may have executed P1 may be thinking it is still running because it started off and then it waited for this gap of 10 milliseconds, and then again it started off over here. So you are making this user perceive that his application or her application is continuing to run. That is the difference between concurrency and parallelism. Clear to everyone? Okay, so this is that CPU time I was talking about. Okay, so it keeps track of how much time did that process took to run, and that it may use it for context switching. Okay, so this is basically the way your memory map will look like. So you have your operating system area in your memory. You have multiple processes running. Each of the process will have context, data, program code, and then each of the context will be divided into the process control block and the stack. The PCB will have three kind of information: the identification information, where you have the PID, PPID, the user who owns the process or application, who the user who has executed the application, and so on. You will have a CPU state information, where you have the program counter, stack pointer, like I said, PSW and other registers. Control information is where you will have the information about the memory unit, memory limits, the open file information, the signal information, scheduling information. Maybe you have created a child process, which I have not talked about. So a process, apparently when you run an application, you can actually create another process within that, right? Which we refer to it as child process. So you can actually run child process from the main process, which information is also available over here. So this is kind of a memory map of how the operating system maintains the running applications.
Sir,
Yes.
sir, you mentioned that while context switching, the operating system will save the state of the CPU of the process to the memory. So
Right.
will it save it to the CPU state info block only? Is it this area where it will store?
It's basically saving this information, right? This whole thing. See, stack is there in the memory, right? Stack is there in the memory, but then some of this information, the CPU state information, is not in the memory. It is in the processor registers. Like, for example, program counter, stack pointer, the registers that it uses to load data and put data back into the memory. If you remember, we looked at assembly code, right? In the assembly code, it was using certain registers, right?
Yes. Yes,
So
sir.
those registers are part of the core. It's part of the processor. It is not in the DRAM. So what it has to do, see, because remember, once you do context switching, you have to save enough information in the memory so that when the process is again ready to allocate the CPU and again ready to start running, you have to have all the information about where you left off your process at, right? Not only the program counter, but even the state of that process, right? What were all the data values which were there in all the processor registers? All of that also has to be saved.
Yes.
Okay, that is the information I am talking about. Okay, now what are the operations that's going to happen on the process? So primarily three, right? So you create a process, right? So when you create a process, it will allocate the PCB, right? And it will initialize certain values like process ID, parent process ID, and so on, right? It will allocate the required resources which process demands, and it will be placed in what we call ready queue. Okay, what it means is when the process is ready to run, but the CPU or the core is not allocated to that process, then it is placed in a ready queue. Okay, then you have a scheduling information about the process. So sir, sometimes some process has higher priority compared to the other processes. For example, if there are certain important operating system processes are there, you want to give it a higher priority compared to the normal user processes. So that information will be used by the scheduling algorithm to allocate the CPU. Okay, and then finally you have the termination of the process, where the process is removed, the resources are reclaimed. Some data may be passed to the parent process. So as I mentioned, you can have the child process which is created by the parent process. When the child process terminates, you may have executed the exit command inside the or exit system call inside your child process, which will return the status back to the parent process. And that is something that also needs to happen at the time of termination. Again, if it is not clear, don't worry. I mean, we have quite a bit of examples down, in this, so you will get the idea. If the child process terminates early or in between or something, the parent process gets informed using a signal called sigchild. Again, we'll come to that when we learn signals. Okay. So while we are doing the creation of the process, while we are talking about creation of process, right? I want to talk about what are the events, what are the situations where the processes are created. So obviously at a boot time, right? So when you're turning on your system, right? Initially, all of these processes will have to be created, and most of the process that you see in the in this PS-AJXF, all of these processes we have not created, right? I mean, I'm not running these applications by myself. All of these processes are started by operating system, right? So there are, like, see the network manager. So this process must be managing my network ports somehow, right? So there are many of such background processes that needs to be time syncing, right? So it is syncing the system time with the network time, with the GMT time. Okay, so there are many such processes which are running, and we call some of those processes daemon process. Why daemon? Because they are always running in the background. Okay, they are always running in the background, and they are doing some activity to make sure that all the system stuff is running. See, all of these background processes we have, right? So there are process for keyboard, process for smart cards, process for sound, process for USB, and many other things. Printer processes, terminal processes. So all of these processes are started by the operating system when the system starts. Then user may request. So we may run an application or program using CLI or by double clicking on application if you have a GUI based system, right? Like I said, you can have a parent process or a process can create another process which we call a child process. There's a fork system call for that. We will learn that in this chapter. Or you may have some batch system that is creating some jobs. Okay, so generally speaking, you can see that all the processes that are created on the system could be falling into one of these categories. Okay, now while we are talking about the system booting, I also want to talk about how the Linux-based system boots, right? So you have to also understand how the whole booting process works. What are the things involved in the booting process, right? So the first thing, let's say you have installed, Linux operating system as your host operating system. Okay, all the devices that you use, all the desktops, laptops that you use, has a memory inside the inside its hardware, which is called ROM, read-only memory. Okay, and these memories are hardwired. They are programmed once only. You cannot reprogram that memory again. Okay, So that memory has a starting of the application booting, and that that piece of code is basically what we call BIOS. So whenever you boot a system, you may have seen an option, press F2 to go to BIOS, right? So that option is basically where the BIOS settings are. Okay, so you can change certain settings. Like for example, you can change the booting order. Meaning, let's say by default, the booting may be happening from hard drive, but you want to change that to boot from a CD-ROM, or you want to boot from USB drive, or whatever it may be, right? So you can do that. You can change the system date and time. Let's say maybe you have moved to a different country and you want to change the default, you want to change the default time zone, right, or something like that. So certain settings are available in BIOS which you can do. In addition, it performs the system integrity check. So it performs checking of all the devices, right? So it will make sure that the devices are functioning okay. So that is the first program that will start running when you boot, which is what we call BIOS. Once it does all of that, then it searches a bootloader in the device from where you need to boot from. So let's assume that your order of booting is USB, CD-ROM, and disk. Now you don't have a USB port in which you have put, you have put the bootable USB drive. Then it will check for CD-ROM. Do you have a CD-ROM? Do you have a CD placed in the CD-ROM, which is a bootable CD-ROM? If not, then it will go to the hard drive. Okay, and it will check the bootloader in the hard drive. So once it finds the bootloader is always at the first byte, starting from the first byte or first sector. So disks are divided into, partitioned into, we talked about that in the file IO, that they are partitioned into groups, and each of the groups are partitioned into sectors. Okay, so it will basically look for the first sector, first page in the disk where the booting can be done from. Okay, where the booting can be. That basically is called MBR, Master Boot Record. So from the Master Boot Record, once the system starts, in the Linux-based operating system, it first runs what we call grub bootloader, or grub, right? Grub. So when you go to your, operating system, and there will be a directory called boot. So in this directory, all the files that are required to boot your system is available. Okay. Now inside this directory, you will see that there is another directory called grub. So when I go to grub, there is a configuration file called grub.cfg. Okay. And let's look at that grub.cfg. What does it contain, right? So what you have to look for is a word called menu entry. Okay, menu entry. So what is this menu entry? Right now, for individual operating system, you may have multiple kernel versions installed, or you may have dual boot done on your system. So for example, you may have a Linux, you may have Ubuntu, as well as you may have Windows. How does the system know which operating system to boot from? So those who have done dual boot, you would have noticed that when the system boots, it gives you the menu. It gives you the option that whether you want to boot from Windows or you want to boot from Ubuntu. Even in the Ubuntu, it will tell you advanced option. In the advanced option, it will tell you whether you want to boot from a kernel. Let's say in my case, it is 5.13.0.28. Another option I have is 5.13.0.27. Third option I have is 5.8.0.48. So you may have different kernel versions installed on the same operating system. So which kernel version you want to boot from? Okay, you want to boot it in a general, generic version, or you want to boot it in the recovery mode option. So maybe your original, some kernel is corrupted and you want to boot from the recovery mode kernel. You can also, so recovery mode basically does not allow you to access certain things like network and things like that. Okay. So what I'm trying to say is that this is the file where it will also have an entry for Windows operating system in case if you have dual boot system. And you can check that. Okay. This is how the menu comes. And once you select the menu, it will start, booting that particular operating system. So assume that we have selected Ubuntu, right? Then it starts from the kernel version that you have selected. There may be a default kernel version, which is the higher most kernel version that you have installed. So in my system case, it is 5.13.0.28. That is the kernel version it will start from. Okay. So what it will do is it will mount the root file system for that kernel. Whichever is the root file system for that kernel, it will mount that. And it will execute a program called init. Init is the mother of all programs, all processes. Okay, so I'm going to show you this particular slide because I want to show you this. So root is the file system that it will mount, or root is the first process run by operating system. In that you have three child processes. This is my init. Any application, including the terminal window, any of the program that you are running as a user, all of them are running in this hierarchy. So every process is a child process of an init process. Every process that is running in a system is a child process of an init process. These two are special processes created by the operating system. This one is the virtual page manager. Okay, and this one is the process swapper or scheduler. Right, so process scheduling is done by this process. The memory management of the virtual memory is done by this process. However, all the other processes that we run are running as part of this init process. And how do we know that? I will show you that on the terminal. So let's go back and run -ajxf, and I'll look for init here. Right, so I'll look for init here, and you will find it here. Okay, so init is the process available in sbin directory, which is the system's binary directory, and you will see what is the process ID of that process. Process ID 1, which is the first process. So 0 is basically your root. Okay, we don't have access to that. 1 is the process ID which runs here, and if you look at any other process which are here, right, they are the child of 1, right? 1. So whichever system processes that are running after init, they all have the parent ID as 1. So all of these have parent IDs as 1, and these are the process IDs of those processes. Okay, so you can actually backtrack your own terminal window also, that it is part of it is in the hierarchy of init. How do you do that? So let's say this is my process ID, right, where I ran my terminal window. This is my terminal window. The parent process of that one is 2547. Okay, so that 2547 is this process, okay, which is this program, and the parent process is 1879. So let me go to 1879. What is 1879? 1879 is this process, which is my system MD. Okay, and that system MD is having the parent process as 1. As you can see, again, we are under init. Right, so the terminal window that we are running is under init. System MD is basically GUI version of the init. So init process was originally designed in the Unix-based environment, very old days, I think somewhere in 60s. And then they included some more functionality, some advanced functionality into that one. So the newer init process is actually called system MD now. Okay. But basically what I'm trying to say is all of the processes which are running, if you try to track back like this, they will always go into init. Init is the mother of all processes. Clear to everyone? Okay. So we start kernel, we run the init process. Okay. Now, when you run an init process has multiple run levels. Okay. So what is the meaning of run levels? Run level means that you can run the init process in different modes. Okay, different modes. What are those modes? The modes are mentioned here, but then I've mentioned them actually in detail over here. So if you run it with the mode of 1 init process, then it is a single user mode. So the system can be only used by one user, which is a root user. If you use 2 run level, then multiple users, but then no network file system. 3 with multiple users, only command line interface, no GUI. Okay. 5 multiple users with GUI with network file system. 6 is the time when you are booting your system. So when the system is restarting and it does not allow you to do any other thing, right? It does not allow you, it does not take your keyboard input, it doesn't take your mouse input, anything. That is the time it is using the 6 as the run level. And if you have a major error in your system, let's say for example your hard drive crashed, or some major device is crashed, and you cannot actually boot your system, then you get the system halt. Let's say you have a memory error, your memory is damaged, or your processor is damaged, or something like that, right? Then you get the system halt. So these are the run levels you have. And how do we know all these run levels? There's a special directory in etc rc, that is where the run level files are mentioned. So if I go, let me go actually here, ls-ltr boot, sorry, not etc and rc, and you can see that when I do rc tab, it gives you all these directory names: rc0, rc1, rc2, rc3, rc4, rc5, rc6. These are all the run levels, and each of these directories will have the respective file for that particular run level to boot from. Okay. This is how your booting works in Linux-based systems. Questions? Okay. Termination of the process, right? So we created the process, and let's say the process is finished, and there will be a termination of the process. The process can be terminated in multiple ways. One is either it falls off the last statement that you've executed in the process, right, just before the last curly brace, or you explicitly write an exit function. So if you explicitly write an exit function also, the process will terminate. This is a normal termination, normal completion of the process. You may also get a fatal error and the process may exit, right? Use either divide by zero error, IO error, memory allocation error, and so on, right? Like I said, the parent process can kill the child process if parent process does not want the child process to continue. In most of the operating system, the parent process and child process are considered as two separate processes, and they are allowed to continue concurrently, right? Which means that if the parent finishes first, child is allowed to continue. However, very few operating systems are such where they don't allow the child process to continue when the parent process finishes. However, all the Unix-based systems that I am aware of, all of them allows child process to continue to run even if the parent process terminates. Okay, so that is another scenario where the termination can happen. The relationship between the parent and the child processes, you could have the resource sharing possibility, right? So obviously when you have a parent process and the child process, you could be sharing certain resources. For example, you could be sharing a data area, or you could be sharing the files, files, open files that you have, things like that, right? So there could be multiple possibilities, and depending on the situation, it will use certain, it will use either no sharing, or it will use partial sharing, or it will use all sharing. Okay. Execution possibility, like I said, parent and child can run concurrently, can execute concurrently because they are allocated different cores, different processors, right? So it doesn't have to run, one doesn't have to wait for another. You have two different processes, they run on two different cores simultaneously, right? Or the other option could be that parent is waiting for the child process because the child process is running and the parent process actually has done, is done doing stuff, right? Memory address space possibility. So again, here you could run a same program, right? So the parent process and the child process can exactly run the same program, same application. However, it is possible that you may want to run a different application as a child process. So you can also do that. You can have a parent process run a different application and a child process run a different application. How to do that, we will look at it in this chapter. Different system calls in this chapter we are going to look at. Get PID is a system call that will return you the process ID of the current process, calling process. Right? The process which is calling that function, the process ID of that process we will get. Get PPID is to get the parent's process ID. Fourth, very important function is what is allowing you to create a child process from a parent process. So when you run an application on a terminal window, it becomes one process. But from that one process, you can actually call fourth system call, which will allow you to create another process. Okay, and that's why instead of creating a process, we actually call it as forking a process. So forking the child process, right? So we fork a child process from the parent process. Exit will be the system call that will allow you to terminate the process. Wait system call, you have to write it in the parent process, and wait system call will allow the parent process to wait for the child process to terminate. So for example, if you have a parent process who have created, let's say 5 child processes, right? So if one parent has 5 child processes created, then for each of those child processes, you have to have one wait system call. Okay. So for 5 child processes, 5 wait system call has to be issued, right? Now you see that we have not provided here the process ID. However, in this another version of the wait, we have provided the process ID. So this version of the wait says that whichever child finishes first, that first wait system call will be out. Okay. So if I have 5 child processes and if the second one finishes first, then this wait call will still come out. If the 5th child process finishes first, then this wait call will still come out. However, here we are specifying for which child we want to wait. Okay, so let's say your parent does not have to wait for all the child processes, but it has to wait only for 1 or 2 child processes which are doing some significant thing. Then you can just provide that particular child's process ID over here, and only for that child it will wait. Okay, and then exec command is the command which allows you to run a different application once the child process is created. Again, I think by just explaining all of these, you may not actually grasp an idea, but once we look at examples of each of these functions, you will definitely get an idea what they are doing. So here again, I'm just showing you the memory map, right? I'm showing you the memory map as to how the fork and the exec function works, system call works. So when you start with your basic C program, right, just basic C program, you have this memory area which is created for a process, right? So you have the context for P1, you have the data for P1, and you have the code for P1. So this P1, why I'm calling it as P1? Because it is a program 1, not a process 1, right? So this is the program 1, right? You have one application running as a process. Now within that code, you have actually issued a fork command. When you issue the fork command, what does it do? Right? It took the memory area from here and replicate it over here. So it's basically the data area and the code area is exact replica of this one. Context area will have obviously a little bit of differences because the process ID will be different, the parent's process ID will be different, and program counter will be different, right, and so on, right? So your certain information in the context area will be different. However, your data area and the code area will be exactly duplicate. But the memory references, memory addresses are different, right? So this child process is running in a different memory area, whereas your parent process is running in a different memory area. What I mean to say is that if you make a change to the global variable over here in the parent process, that change will not be available in the child process once the fork is executed. You have to keep that in mind. If I make a change to, let's say before doing fork, I had a variable called I. So there will be copy of I here and there will be copy of I here. Now, if I make a change to the variable I here, let's say I equal to I plus 2, that I plus 2 value will not be available over here. Okay, so even though the variable name is the same, it has two different memory locations after you do the fork. One for the parent, one for the child. Please keep that in mind. So now what happened was that the same program P1 is running in two locations for two different processes. You run an exec command. Let's assume that in this code, there is an exec command which is there for child process. And then when you run an exec command, you provide the program name. So what this exec command will do, it will take the application code from the disk and it will load it into the memory here. So which means that the data area and the code area, which was there for this P1 program, will be replaced by the P2 program, another program. Okay, this is how you can actually run a different application in a child process. You can also do the other way around. You can also say that P2 can run here and P1 can continue to run here. You can also do that. It doesn't have to be always a child process gets a new program code. Even the parent process can do that. Okay, so this is how your fork and exec works. Now I want to talk briefly about the process state. So we talk about how the processes can be created, but then whenever each of these processes are created, it goes through certain state changes depending on what is happening with the process. So when the PCB is just created and the resources are just allocated, right? So while that initialization is happening for the process, it is in the idle state. So the state of the process is called idle when the the PCB, the stack, and everything is just being initialized. Once the initialization happens, once all the resources are available to the process, and it is ready to be allocated to the core, right, or CPU or processor, whatever you want to call. All these three are kind of synonym, right? Processor, core, CPU. So once it is done, you put that process in what we call ready queue, and that process becomes runnable or ready, right? So process now is ready to be allocated a CPU. Once the CPU is allocated to that process, the process starts running, and therefore the state changes to running. Now let's assume that in the process, you have some major IO activity that you are doing. Let's say you are reading a big file or maybe sending a lot of data on the network or something like that, right? So now the process is not going to waste. The operating system will find out that there is a major IO activity that needs to happen, and process has to wait for that IO activity to finish. Okay, so as we said here, right? So 10 milliseconds time is given to each process. But if that IO activity is going to take, let's say, 10 seconds, you can't have other processes waiting for that 10 seconds. So what will happen? Context switching, right? So the process will be deallocated the CPU and the process will go into the sleeping mode. Okay, so the process will put into the sleeping mode. So sleeping mode is where you will be basically waiting for some major IO activity to finish or some major activity event to happen, right? Once that event is finished, and once operating system knows that okay, data is available now for the application, and application now can read the data and do whatever it needs to be done, or maybe it was writing the data, then the writing is done, then again the process goes back into the ready queue and it becomes runnable. So this is the cycle which will continue when you have a major IO kind of activity or some event on which the process needs to wait. Now, if the process is taking longer time to run, right, and no IO activity, but it just requires more CPU cycles, then you have to do context switching at some point, right? So that there is a signal, there is some message that is sent to the process by the operating system that says that, hey, you need to stop running, right? You need to stop running because there are other processes I need to allocate the CPU, right? So I need to get the CPU from you and I need to allocate that CPU to somebody else. So the process will be getting signal, and so the process goes into the suspended mode. So the suspended mode is something like a pause mode, right? So we are not actually stopping the process, but we are kind of pausing the process, and the process will be in the pause state until again there is a time for that process to go back and allocate the CPU again, right? So process goes from running mode to suspended mode. When the context switching happens, it goes back to ready. Once again, that process, once again, operating system decides that this process again needs to get the CPU. So it goes back to ready state, and then again this cycle continues. Once process is done running, right, the process has finished, then the process will run an exit command, either explicitly or an operating system will run it for the process by default, even if you have not run an exit command internal to the code, inside the code, right? But that exit command has to get executed. And once that command executes, the parent process, right? Parent process must read the status of the exit. Until the parent process reads the status of the exit, that process will be zombified. That process will be zombified. So basically the process, even if the process is finished, but if the parent process has not read the exit status of that process, then that process is in the zombified state. Once the parent process reads the exit status, then the process is terminated finally. Okay, so this is how the process states works. Now let me just briefly show you how the fork works, right? So we have seen the status life cycle of the process, and we know that we can have a child process and the parent process by using the fork. So we want to see the example of how do we create one. So you have a main function, and you have this PID variable declared, and then I'm printing the process ID of the current process and the parent's process. So till this point, I just have one process, right? I just have one process, no parent, no child. So it is basically this particular state over here. This particular state, right, is what I have here. That there is no parent or child. So that's why I'm calling it as an original process. So it is not a parent, not a child, it is an original process. Now I issue the fork command. So fork is the only function, only library function that is returned 2 times. So no matter whichever library function you look at or user-defined function you look at, that function will return only once. But fork is the only system function which is returned twice. Okay, and why twice? Because one return is for the child process, another return is for the parent process. So basically what happens is when you issue the fork system call, primarily it takes this information, duplicates it over here. And then one return will be done in this code, another return will be done in this code. That is what that fork command does, fork system call does. And you see that there is a return value over here. That return value is the process ID coming out of the fork, returning out of the fork. Okay. So in the parent process, the PID value returned will be the PID of the child process. Why? Because the parent cannot know the child's process ID. Okay, so in the parent process, when the fork returns in the parent process PID value will be returned as the child's process ID. But whenever the fork returns for the child process, the PID will be returned will be 0. Okay, so fork will return 0 value in the child process, but in the parent process it will return positive integer, which is the child's process ID. So now what we can do is we can actually write a condition. Using that PID value, we can write a condition and we can say that if the value is not equal to 0 or greater than 0, then it means that this condition will only be true for the parent process. Okay, so if this condition is true, then this condition is going to be true only for the parent process. So whatever I do inside this brackets, that piece of code will only be executing for the parent process. However, else part, or I can check for equality of 0 here. In that case, that process is going to be the child process. And therefore, anything I do here, it is going to be running only for the child process. So you can see that after 4, you have 2 processes running. And you can control which code, which process will run will depend on this condition over here. The return value from the fork. Because there are 2 different return values. One for the PID is greater than 0 or a positive integer value, which is for the parent process, and this is for the child process. However, this line is outside of that if else statement. So the question is, which process will run it? Well, the answer is both. See, whenever you put any command outside of the if else statement, both the process will have to run these. Okay, and if you put it inside if or else, then only one of those processes will run it. Okay, so let me just run this code briefly and explain the output, but in detail maybe we can look at it in the next lecture. So you can see that this is my original process, which is the PID 3271. This is my parent's PID, which will be the PID of my terminal window. So you can see that bash is the terminal window 2558, which is my parent's process ID. Because in this terminal window, I'm running this process, and this is my process ID. Okay. Now when I do fork, I'm running after the fork. If the PID is not equal to 0, then it is printing these 2 things, which is basically my parent process, right? So inside my parent process code, I'm going to again print my process ID and the parent's process ID, and I'm going to print the child's process ID. So if you see the output, I see that the original process now became the parent process. The original process became the parent process, and also the same parent or the same PPID, right, for the parent process. And the child process ID is 3272. This is 3271. Okay, and this process ID is 3272. And now the parent process is actually running in a different core, so it finished. Now the child process must have been allocated a CPU, and the child process started running the else part. Why? Because this condition was false for the child process. So in the child process, it is just running this line, right? And that is what this is doing. Okay, so you can see that this ID 3272 here and 3272 here are matching. This line is coming from the parent process code. This line is coming from the child process code. And you can see that this particular line is printed twice, one for the parent, one for the, one for the child, because that line is actually the last line, which is this one, right? And which is being printed by or executed by both the processes. Okay, so this is how the process management you can have the parent process create the child process, and then here you can do whatever code you want to write. Here also you can do whatever code you want to write. Depending on that, it will basically execute those processes or that piece of code in a separate course of separate processor as a separate process. Let me stop here. Any questions? This aspect is very, very important. So if you had difficulty understanding it, please revisit this lecture. Please review this lecture and try and understand, right? If you're not able to understand, please ask me questions in the next lecture. I'll try to make it a bit more clear if possible. Okay, any questions? Okay, so thanks everyone, and I'll talk to you guys on Thursday.
Sir,
Yes.
so in the PPT you have written PID_T then get PID function, right? So like, do we have to replace this PID_T with something in that PPT, sir?
In the PPT. So actually, I just pasted the code from that file
No,
over
not
here.
the code,
Where you are
like,
talking about?
no, while you are explaining this process is like this process does this thing, maybe
Ah.
some slides earlier.
Yeah.
No, sir. Still more.
Yeah.
Yes, yeah. So like this PID_T then get PID. So like this PID_T is to be replaced by something, or the
No,
system will do it.
no. So this is the function forward declaration.
Okay, like that is the output.
Yeah, the function forward declaration in the header file.
Okay, right.
So
Right,
a
sir.
PID_T is the type of the data this function is going to return. That is what this is saying.
Okay, sir. Yes.
So PIDT. So if you look at the header file types.h, so I've included this file here, right? Types.h. If you go to this header file and search for PID_T, you will know what that data type is.
Okay,
Okay,
sir.
that is just a return value data type. That's all it is. Any other question? Okay, thanks everyone.